Good morning.
Good morning.
Today's lecture we will start on chapter 8, which is the electrical power system. So what we discussed in previous chapters are related to circuit analysis, or how to solve some circuit problems, or basically I would say like the ABCs of electrical engineering, or basic ABCs. Then we start doing some analysis, like creating some words that have meaning. Now we would like to use these words as a sentence, as a useful sentences. In other words, we would like to use what we have learned before in electrical engineering, fundamental electrical engineering course, as an application more than as just a circuit without knowing what's this circuit. So previously, when we did the first and second exam, we used to have a circuit and we didn't know what it is, or how can we use this in real life. Now we will try to model some practical things that we have, some devices like a motor, a transformer, for example, as we'll discuss later, like operation amplifiers, different types, generator. So we will see how we can model this to find an equivalent electrical circuit model. After that, we can use this in real life for, or we can apply the circuit techniques that we learned before, KVL, KCL, Ohm's law, power analysis, complex power, real reactive power, all of these concepts that we learned. Now it's time to use them for some useful applications. So for chapter 8, it's electrical power system, we will go first through the three-phase system. So the three-phase system is basically same circuit technique analysis that we know, but we will apply it for multiple phases, or something we call a three-phase, which is basically we will apply the same context, but now times 3. Then after that, we will go to the transformer. Then we will start discussing the motors. That's the plan on chapter 8. Okay, so what does three-phase system mean, or polyphase system mean, and what's the importance of using this? Okay, when we are, or as we know from circuit analysis, and even like in previous lecture, the electricity that connected to our home, or electricity that we are using it, are based on AC, right? So we have the AC power at the frequency 60 Hertz. It's most like cosine waveform. And the magnitude, it can be either 120 or 240 that's connected to your home. While in the distribution area, it can be like for 7.2 kilovolts. It can be for medium voltage as 11 kilovolts or 12.47, whatever, and we have high voltage like 115 kilovolts, 230 kilovolts. So we have high voltage, we have something we call it extra high voltage, 400 and above. We have high voltages between 400 to 100. We have low voltages, I think it will be between 60, medium voltages, between 66 volts up to 12, or I would say 33. Then we have the low voltage of 7.2 kilovolts and down and below. That's overall for the power system. And we say the power system is the electrical system connection that we connected to our utility, our electrical utility. Then, as we know, the power is a function of both currents and voltages, right? So the overall power system, we're going to assume the voltage is constant. So when we are dealing with the residential, like with the wall plug, the power or the voltage is fixed, 120 volts. And as we discussed last lecture, the power connected to your home is either 120 or 240. I'm sorry, the voltage is connected there. So whenever you have, look at the voltages, it's fixed, it's constant. Every time we assume the voltage is known as 120 or 240, or if you are industrial load, 480, etc. So whenever we are dealing with any type, we will assume the voltage is known. So when we go to the power lines, and if you know that type, what's the power line, or then you know what the voltage is. For example, 132 kilovolts. What's the thing that we don't know is the current. Why we don't know it? Because the current depending on the load. We know as the relationship between, again, the power, S bar equals V bar times I bar conjugate, right? So V is constant. So we will realize that S bar is directly proportional to the current, right? Let's talk about the magnitude. Yes, that's what we have in the math. Then, when we increase the amount of power, this means we will increase amount of currents. The currents we don't know, or the current is changing depending on the load. The load in the morning is not the same as in the afternoon. It's not the same at noon. It's not the same at evening, right? It's changing. Therefore, the current will be changed depending on the load status. So, most likely, again, we will assume the voltage is known. Then the impedance it can be like also changing depending on how many devices are connected. Then most likely the larger loads or the larger power consumption, the larger currents will be. So this can do some limitations on us. Also recall last lecture when we talked about the AWG. AWG 10, it can handle 30 amperes, AWG 12, 20 amperes, something like that. So AWG means each wire or each conductor has its own ampere capacity. And that ampere capacity, if we exceed this will cause overheat for the conductor, and that overheat will cause damages, sometimes causes fires. So we don't prefer to make an overload for the conductors. Then there is an ampere capacity. So there is some current capacity, current limits for each conductor that we cannot exceed. So let's talk about then, as I mentioned, like in residential home, we have 20 amperes or sometimes 30 amperes. Then this is something also you can imagine it as the water pipelines. If there is a large demand of the power of the water pipelines, you need to have a larger thickness, right? Replace that pipeline by a larger thickness. Increase the radius, then you can have more water, right? Or you can install another water pipeline to supply your demand. So now the concern is, yes, power is directly proportional to the currents, but I cannot increase the current forever. I cannot say, okay, I need more power, let's increase the amount of current as much as I want. No, because there is a current capacity. So let's assume we have two conductors like this way. We have phase or that voltage source connected to the load. Then we have two conductors, live and neutral, as we see in this diagram. And assuming the ampere capacity, which is again, S is directly proportional to I, let's assume that after doing several calculations, this conductors can supply only 1 kilowatts as a roughly number. So let's assume after several calculations we can, for this system, the maximum power that we can get is 1 kilowatts. Assume that load is 2 kilowatts, not 1 kilowatts. What should I do to supply that load? What do you think? I want to hear from you. What do you think? How can I supply a 2 kilowatts load while the system, the conductors that I have are based on 1 kilowatts? Any thoughts? Yes?
Add another wire in parallel.
Add another wire. That's a great idea. So we can basically, I would say, like, we can divide the loads into 1 kilowatts, then add another wire. Is there any other idea? Oh, this is a great idea. Is there any other? How about, yes? Yes?
Go to the next step up in the voltage.
Increase the voltage
The next, like,
to the next level. That's good, but the thing which is assume the devices that you have are based on 120 volts or 240 volts. So increasing the voltages will not be compatible with the devices with the load. So increasing the voltages is good, but unfortunately it will be incompatible with the devices. So yes.
increase the wire diameter.
Increase the wire diameter. That's another approach. Which is, again, you can imagine this, that you need You are supplying your home by water, and you have a large demand of water. So there is one way by connecting a new line, a new water line, new water pipelines, or increase the diameter for the water pipelines connected to your home. So economically, removing the existing one and adding a new one with larger diameter might be expensive. And the other thing, which is the overall hit cost, which is basically you are connecting the power lines based on the infrastructure of the towers, the infrastructure of even the weights of the wires. So if you increase the thickness, this will increase the weights, will affect on the mechanical structure of the towers. So it can be very expensive because we need to modify all of the power lines, all of the power lines, utility poles. We need to modify them so it can handle that large amount of thickness. So yes, also it's a good idea to increase the thickness, but unfortunately it will be very expensive. So we realize here so far the best thing to get 2 times double the amount of the power by doubling the amounts of the circuits. Doubling the circuit, or in other words, by doubling the costs. Is this correct? Yes? That's what we have. Now let's assume, or let's think about it. Is there any other economical solution than doubling the power, doubling the costs? Can we find a way to make it more cheaper than that? Yes, we can. How? This is positive, this is negative. This is positive, this is negative. Can we make a common negative? Yes, we can. So, that's what we did here. And instead of doubling the circuits, we can have a common neutral or common returning currents, 2 live. So the first live we'll call it phase A, second live phase B, and the neutral is the common. What's the advantage of it? We have 3 conductors, so basically 1.5, 1.5 times the cost will yield to 2 times the power. Which means I can save more money, right? Yes, it seems here, which is I have 3 conductors and 3 conductors. And instead of using 4, I'm going to use 3. And here I'm doubling amount the power by using 3 conductors. And when you connect this for very long distance, for 100 miles, this means you're going to save a lot of money, right? Then this thing is called 2-phase or polyphase or biphase. Biphase, which is basically phase A, phase B, and the neutral. But when we look at biphase, can we find a cheaper option than that? That's another question, or that's another way of thinking. So, can we find a cheaper? Okay. How can we find something cheaper than the biphase? Biphase 1.5, 1.5, the cost will double the power. So the answer, yes, we can find, and it is based on the 3-phase. Okay, what does 3-phase mean? So in 3-phase, we can say we can have 3 conductors and 1 in neutral. So this is phase A, phase B, phase C, and 1 in neutral. So all of these phases are positive and the neutral is negative. So 1 returning currents and 3 positive currents. So 3 conductors. So here is the load side, here is source, here is the load side. So we realize that we can have 4 conductors. Then we will get 3 times the power. Okay. In other words, 2 times the cost will give us 3 times the power. So this is even much cheaper than when we talked before at the biphase. 1.5 costs times the cost will yield to 2 times the power. Just increase another half cost, then you can triple amount of the power, which is something great, right? Then that's the three-phase. So we realize the three-phase, it's even cheaper than the single phase. I'm sorry, the biphase. Biphase, cheaper than single phase. But three-phase is even cheaper than that. Okay. Now, with this situation, we will assume a phase shift for each phase. So the phase A, we will assume the angle of phase A is 0 degrees. The angle of phase B is negative 120 degrees. The angle of phase C, positive 120 degrees. Why we assume these angles? Basically, I will say it is 360 divided by number of phases. So 360 divided by 3, this yields 120. So the phase shift between phase A and B and C, there should be 120. Again, we will discuss this later, but here just for your information, we choose 120 as a phase shift. Again, we will discuss in details later today's lecture or maybe next lecture. So we just keep in consideration that the phase shift between each phase is 120 degrees. The magnitude of the voltage will be the same. If it's 120, all of these phases 120, but phase shift is 10, the other one 180, the other one negative 120, and negative 120. Now, with the three-phase, we found the life is much easier. So we can connect 3 times the power by doubling the cost. And even we realize when we connect the power for, we call it transmission lines and high voltages, where we will not connect the load. If we connect if you distribute or if you transmit the power from one side to the other side, and there is no connection, no overload connection, basically during the high voltage scale, we can avoid or we can get rid of the neutral and we can use only 3-phase alone. We can say that let's use phase A, B, C without neutral. We will discuss also this approach in deep details, how to avoid using the neutral, but I'm just telling you about the technology now, and as an overview, then let's go into details. So basically, we realized in 3-phase, we can use 3 positives or 3 conductors to supply the power. And we don't need to have a neutral. This means we can save more money, right? Then the 3-phase works great. This one works great. Now, one more question. Is there any cheaper option than the 3-phase? Okay, battery. 4-phase. We prefer to use odd numbers, so we can. I would say 5-phase. Can we replace the battery? Okay, so we have cheaper option than 3-phase. 5-phase. Again, we prefer to use odd numbers. 5-phase, 7-phase, 9-phase, etc. So we have 5 phases, and that 5 phases we will have 5 conductors. 1, 2, 3, 4, 5. Phase A, B, C, D, E. Then we have the neutral. And the phase shift 360 divided by 5, then you can determine the phase shift between each one. Okay, in 5-phase we have 5 positive and 1 returning current for the negative, for the neutral. So 5 phases means we have 1, 2, 3, 4, 5, 6 conductors, then 5 times the power. Or in other words, 3 times the cost, you will get 5 times the power. Then this means this also we can save more money more than the 3-phase, right? Now the question is, our electrical utility, is it based on single phase, biphase, three phase, five phases? Three phases, right. So why? We just said that five phase is better. Why we use three phase, why not five phase? Yes?
We don't really need five phase. None of the stuff that we operate is going to be consuming that much power.
Sometimes we really need like much power. But I would say like, let's think about it in economical solution. So here in mathematics, we see like 3 times the cost equal to 3 times the power based on the conductors. But do you think this is the only solution? I mean, this is a good approach to say 3 times the cost based only on the conductors? Okay. Let's think about the power lines where we have a large utility poles or a large towers. So are you familiar with these towers, these big towers, right? So these big towers are based on the three phase. Okay, so you see they take a large size, and this is based on three phase. If we have five phases, this means we will have a larger power size, power tower size. This tower, if it is going to be larger and larger and larger, this means the overhead cost in building that tower. You need to have more steel, you need to have more concrete in the bases, you need to have these kind of towers, they need to have a large thickness or a large capability of handling these loads. So I think, some of you are mechanical engineering and you know about the loads more than me, which is how can we handle the weights, how can we handle or the overall structure. So basically, when we have five phases, this required a very expensive tower to build, which is way expensive than the three phase. So we realized, okay, five phase can provide higher power, but the overall cost, three phase will be cheaper. So the benefits that we will have from five phases will not be significant. And in the same thing when we build the transformers, building the transformers based on five phases requires a very large size transformer, and this will be a big challenge. So in summary, theoretically, five phases is better than three phases. But practically, unfortunately, we cannot do that, which is very expensive. Now, we see some applications are based on five phases machine for only research and development. So you can see, especially on some industrial loads, we have some five phases induction motor. Five phases, some part of motors. Those are for research and development, but they are not actually practically applied. I mean, you might have some, or you might see a lot of research about it, but we are not using it in real life as commercial thing, or like sell thing, or let's say, let's use this in real life, or let's use this in production line, etc. So again, five phases, we are using even like some small grid connection for five phases, only again under research and development, but we are not applying it for overall life, because when we have a big towers, big infrastructure, big costs, and also we need to purchase a big land for these towers to supply the load. So we realize that five phases is not applicable because of the size, the cost. Okay? Now, is there also theoretically cheaper option than the five phases? 7 phases. If you keep up, you will get larger amount, 7 phases, or 9 phases, 11 phases. When you keep up, again, theoretically we will realize we will save more money by tripling or double or 5 times the power, 7 times the power, 9 times the power, etc., by saving more costs. But unfortunately, the problem is all of this cannot be applied. Okay? How to apply this. So we realized the optimal solution, so we can save more power with lower infrastructure costs as a trade-off. We realize the optimal solution is the three-phase. That's why the existing system is based on three-phase. Then we realize that the three-phase is working great. And actually also the three-phase has been invented by Nikola Tesla as well. And Nikola Tesla, when he invented after he invented the AC and winds, and remember when I told you about the war between AC and DC, AC wins. Nikola Tesla didn't stop and say, okay, I win, and that's fine. He keep inventing more by inventing the three-phase, and he said that the three-phase also, we can save more money by tripling amount of the power. Then this makes also the AC more dominates. Then we all of the infrastructure of the power system is based on the three-phase. That's why we have here over the whole world, not only in the States, and it's in every country in the world, it's based on the three-phase system. Okay, any question about this overview? Yes?
So is it always on, so we always have one neutral wire?
Yes, one neutral wire. Then again, the phase shifts between any phase will be 360 divided by number of phases. So 360 divided by 7, 360 divided by 9, 360 divided by 11, etc. That's how we determine the phase shift. Any other question before start going to the three-phase system? Okay. Now, since the existing power system based on the three-phase, then it will be useless to discuss what's 3-5 phase, what's 7 phase, what's 8 phase, 9 phases. This can be some advanced topics, or 5 phases. It's been used in research and development. So this can be very advanced topics only in electrical engineering specialist area. Now, the balanced three-phase system. And it's very important to look at the word balanced three-phase system. Okay, now I told you the three-phase system. We have three wires, 3 conductors, and 1 neutral. But you need to just pay attention at the word balance. What does balance mean? You know your home is connected to single phase, right? Because your home is connected to phase A and the neutral, which will go to the transformer. That transformer will convert from 7.2 kilovolts to what? 120 or 240. Let me just show you this. We have 3 phases from the utility. Then it will be connected to the transformer. We have 3 transformers, 1, 2, 3. Each transformer will be for each phase, from 7.2 to 240 or 120. Then 240 or 120 will go to your home. So what's connected to your home is one of these transformers. Then your neighbor, let's assume this transformer on the left is transformer A, on the middle B, on the right C. So you are connected to transformer A, your neighbor B, your other neighbor C. Even though, let's assume that your home are identical, the same square feet, the same area, the same loads, but we cannot guarantee you will consume the same amount as your neighbor. So you might run on the dryer, the washer, while your neighbor maybe turn on the AC, the other one maybe is leaving the home, so the power is off. So this will make some mismatch, or something we call it unbalanced system, which means phase A consumption is not the same as phase B, is not the same as phase C. And this will create some problems into the electrical power utility when we have unbalanced or unequal load consumption. How can we avoid this? For overall large scale, they will try to supply an equal amount of loads to the same system. So I would say for this neighborhood, for a specific neighborhood, let's say for phase A, we're going to connect 10 homes, phase B, 10 homes, phase C, 10 homes. Then we will say like the overall average of phase A will be the same as overall average of phase B, the same overall average of phase C. So we are working on based on average power that how they can consume. Then there is a small amount of percentage, unbalanced percentage can be allowed, up to 3%. Sometimes it can be violated up to 5%. If there is a 5% unbalance between this, more than 5%, then we need to take an action. So we can make some studies and say maybe phase C has lower loads than others, then we can connect additional home to make sure to maintain the balance. So again, overall thoughts to remove or to overcome some problems that we have in the power utility, we are trying our best to make it as balanced as possible. And again, balance mean identical loads, 3 identical loads. Phase A, phase B, phase C are identical. So as a result, when we discuss here in our analysis the three-phase balance system, we are going to assume these loads are identical. 3 identical loads. Okay? Then we can overcome all of these problems. The other thing, since we say it's balance, we're going to assume the voltage of phase A, the same as the voltage of phase B, the same as voltage of phase C. All of them the same magnitudes. So, same voltage magnitudes. So the first condition for the balance, the first thing, 3 identical loads. The second thing, same voltage magnitudes for all 3 phases. For all 3 phases. Which means if phase A, if your home connected to 120, your neighbor must be 120, the other neighbor must be 120. And that's normal, that's what's supposed to be. The third thing, which is phase shift 120. This is a must. Phase shifts 120. How we get it 120? It's basically 360 divided by 3, then it's 120 degrees. In other words, you are connecting at phase A with angle 0, 120 volts, angle 0. Your neighbor will be with 120 volts, angle negative 120. The other neighbor, 120 volts, angle positive 120. So when you have different angles, this will not impact the load. The load will run with any angle, there is no problem. But here, we put this angle, or choose this angle as 0, 120, negative 120 in purpose. Why? What's the point of using this phase shift? Why wouldn't use them as zeros and stop? You can imagine this as a vectors. You know, in physics or even in math, like this is vector A, and with angle 0, vector B with angle negative 120, vector C with positive 120. Okay? Let's assume this vector is like this, A, B, C. So imagine that there is an object in the middle at the origin, and assume all of these vectors A, B, C are equal in magnitude, while the angles are 120, 120, 120 between each one. What will be the net force? 0. Excellent. Why it will be 0? Because just try to push this way, this way, this way, this way. Or in other words, try to put in the calculator as 120 angle 0 degrees plus 120 angle negative 120 degrees plus 120 angle positive 120 degrees. And of course, the answer will be 0. Okay, what's the point of this? Why we do this? To get a 0 net. Where the 0 net will be? This is the 3-phase connection. We have phase A, B, C, and the neutral. What's the neutral current will be according to KCL? I neutral will be IA plus IB plus IC. And since it is balanced, it's going to be as I angle 0 degrees plus I angle negative 120 degrees plus I angle positive 120 degrees. Again, this yields to 0 amperes. Then, so we put this in purpose to let a 0 neutral currents. That's why we do it. So if we assume all of them are the same thing, if we assume all of them with angle 0, this means I angle 0 plus I angle 0 plus I angle 0. This here means 3 times I angle 0 degrees. What does this mean? 3 times the currents will be following in the neutral if we remove the phase shift, if we assume there is no phase shift. So this means the neutral current will be high, will be very large. And this means the conductor of the neutral cannot handle it. because 3 times the currents will make the neutral heats, and this will affect the neutral, which is something that we don't want, because high neutral currents, high ion neutral is undesired. Therefore, we choose to have a phase shift so we can get something as 0 neutral currents. How can we take the benefits of this? This benefit will allow us to sometimes, since the neutral current is 0, let's remove the neutral. Why we need to use it? In some applications we can remove it. As we will discuss again, we will discuss this next lecture, but here just I'm telling you that we are trying our best to make the neutral current as low as possible. So I would say if the system is balanced, if 3-phase is balanced, so what will happen? I neutral will be 0. Okay? Now also keep in mind there are, how can we know it is balanced or conditions to be balanced? When we say balanced, there must be 3 things satisfied, which is 3 identical loads. Then we have same voltage magnitudes. Then we have 120 degrees phase shift. These 3 conditions must meet. When you read any statement, it says it is balanced. If you see any statement, is it balanced or not? Then you need to check these 3 conditions. 1, 2, 3. Those are the balanced conditions. That's how you test the system, is it balanced or not. Okay? Does this make sense? Now, I mentioned the phase shift is 120 degrees. Is this correct? Okay. Now, how can I distribute this? Most likely, we will pick up phase A as a reference. As a reference with phase shifts 0. That's what we will do in 3-phase system. We will assume phase A with phase shift 0. So here is phase A, phase shift is 0. So since the angle is 120, what's the phase B will be? Are we going to make it positive 120 or negative 120? Here is the concern. So we will say that we can have 2 options. We can have one option by saying that phase B will be negative 120, phase C will be positive 120. That's one option. The other option, by swapping this, phase A every time is reference. So we will say phase B positive 120, phase C negative 120, and all of them are in degrees. So we have 2 options. Which one is correct? Which one we are using in real life? Actually both. How can I distinguish which one that we are using? The first sequence is called positive sequence. Or in other words, ABC sequence. The other sequence is called negative sequence. Or in other words, it can be called ACB. So you need either to memorize this. Positive sequence ABC, negative sequence ACB, and how is the angles for each one? Because we're going to use this a lot. Not only in 3-phase, we're going to use this in the motors, we're going to use this in the generators as well. Positive sequence or negative sequence. Every time phase A is 0, then negative sequence or positive sequence will determine the status. So, and remember, all of them are sharing the same magnitude. So let's look at the notes written here. We have positive sequence ABC, negative sequence ACB. So I prefer to use ACB, not CBA. I don't like ACBA, but whatever. How can I memorize this? By looking at the angle. You can imagine this. This is with angle 0. This is negative 120. This is positive 120. This is angle 0. This is negative 120. This is positive 120. Okay? ABC, ACB. Or in other words, you can imagine this in different way. Like, try to make this. So here is phase A. Since it's negative, here is phase B, here is phase C. And here is phase A, here is B, here is C, depending on the positive or negative sequence. So travel clockwise. Clockwise from A to B to C, right? This is positive sequence. From alphabets A, B, C. When you travel, even here clockwise, you will see A, C, B. Negative sequence. A, C, B. Let me write them as upper cases. Okay? Or in other words, in order to get the alphabets correct, you need to travel counterclockwise to get ABC. Right? So in other words, this means the top is the opposite than the bottom. Right? That's why the one is called positive, the other one is negative sequence. So the overall thoughts, again, just make sure the angle of phase A every time is 0, B negative 120, C positive 120 if it's positive, if it is negative swap B and C. Then that's it. And they are all sharing the same magnitude. So let me go back to this chart a little bit and just discuss some. These are the power lines, 3 power lines and 1 neutral. So depending on the currents and the voltages, we have 4 currents. Current of conductor A, current conductor B, current conductor C, neutral currents. Regarding to the voltages, since we have 1 neutral and all of them are positive, so we have positive, 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 and 1 negative, which is the neutral. So we have VAN between conductor A and the neutral, VBN conductor B and the neutral, VCN between conductor B, C and the neutral. Okay? So therefore, we are calling that we have 4 currents, 3 line to neutral voltages. Okay? We say this as line to neutral. Line to neutral. Voltage. Voltages, this means we have VAN, VBN, VCN. And don't forget bars. So that's the source from VBN, VAN, VBN, VCN. Live can be either A, B, C, can be any of A, B, C. Neutral is the negative returning currents. Okay? Or returning, conductor. When we have 4 currents, 4 line, IA, IB, IC, then we have a neutral. Okay? Just look at this diagram, then you can get used to it. Now, how can we find the analysis? If it is balanced, again, this happens if and only if balanced, then you will see all of them sharing the same magnitude. But for positive sequence, it is, you see the sequence 0, negative 120, positive 120, negative sequence 0, positive 120, negative 120. Okay? Does this make sense? Here, just keep in mind, it is for balanced system. Now, how about the currents? Again, it is balanced system. So balanced 3-phase, this means all of the currents will be equal to each other. According to Ohm's law, I equal V over Z. Since Z is identical, this yields to the currents to be balanced. So IA, IB, IC, they are all will be equal to the same amount of currents. Then what will happen to the angles? We will not say phase A current will be 0. It will be with angle theta. We don't know. It might not be 0. We just assume the voltage is 0, not the current angle. The voltage angle is 0, not the current angle. So we put theta just in case what it is. Okay? Then what will happen to the others? Negative 120, positive 120. Other than that, the magnitude is the same. So when you do the calculation, you can calculate phase A, then phase B, just put negative 120, phase C, positive 120, if it is positive sequence. If it is negative sequence, just swap between A and B. B and C. Okay? That's how we do the formula. Again, they are all sharing the same magnitude, if and only if it is balanced. And for this course, we will assume every time it's balanced. Now, how can we convert this to time domain expression? We know for time domain expression, V, for example, in single phase, it is V RMS angle alpha. So we used to say V of t equals square root of 2 V RMS cosine omega t plus alpha, right? That's what we used to do in single phase. In three phase, the same way. So VAN cosine omega t, but there is no plus alpha because we used to assume the angle of VAN is 0.
Right.
Because VAN bar equal VRMS angle 0, right? That's we say cosine omega t plus 0. Okay? How about phase B? Just since it is positive sequence, I'm assuming it's positive sequence. Since positive sequence, A, B, C angle 0, A with angle 0, negative, B with angle negative 120, C with angle positive 120. That explains why we have angle negative 120 here, here angle positive 120 here. Other than that, they are the same. Just phase AN, VBN, VCN. How about the currents? The same way. Here again, we're assuming it's positive sequence. Therefore, for negative 120, we'll make this phase B negative 120. For C, positive 120. So we are repeating the same thing 3 times. But the thing which is keep into consideration, the phase shift. Again, here I'm assuming positive sequence. If it is negative sequence, it can be also something different. Okay, now there is something other than the voltages that we call it from line to neutral. There is other type of voltages called line to line. We used to say put the negative at phase B, phase neutral. That's what we used to do, right? Then we put one positive at A, one positive at B, one positive at C. That's what we used to do. Now there is another approach for the voltages. How? We can make the voltage between A and the neutral, B and the neutral, C and the, A and B, B and C. What do I mean by this? Assuming the voltage positive at A, negative at B. This is called VAB. Assume the positive at A, at B, the negative at C. This is called VBC. Assume the positive at C, negative at A. This is called VCA. So there's another definitions of the voltages by not using the neutrals. That's why it's called phase to phase, or sometimes we call it line to line. So here we will not using the neutral line. Don't use the neutral. By not using the neutral. So how we can do the calculation? VAB equal VAN minus VBN. VBC equal VBN minus VCN. VCA will be VCN minus VAN. We will discuss more details about this, but this is the life to neutral. Next thing we will talk about the balance formulas about it. Next lecture. And